Hello students, welcome back. We completed section 1. Now let's go to section 2, linear functions. A linear function is a real function defined like this in ax plus b form. Well, that's the definition our textbook author is using, and I agree, and I'd like to follow that, but there is an issue. There is a possible ambiguity that may cause some confusion. Some people impose an additional condition like this. The leading coefficient a is non-zero. Why? Because a is 0, then ax is 0, so this entire leading term drops out and you have a constant function. F of x is equal to b. And that's not linear, some people argue. Other people disagree. It's okay because even if we drop this ax and we end up with a constant function, f of x is equal to b, its graph is still a line. It's a horizontal line, but it's a line anyway. So you can call it a linear function one way or the other. Well, both are okay, but our textbook author follows the first convention. Actually, the second convention, excuse me. Do not specify one way or the other, so I'll follow that. So I'm going to consider horizontal lines into the mix as well. The vertical line, on the other hand, that's not a graph of a function, so that's out. So horizontal line is okay. Whenever a is 0, slope is 0, then we have y equals to b, a constant function b. That's good. That's okay. But vertical line x equals to a, that's not okay. So as long as a line is not vertical, we have something called a slope. In this case, it's a value, and then the y-intercept, which is represented by b. Here are some visualizations. Well, let me use m in place of a, which is a little bit more typical as a matter of fact. Here's an example. You can express a line or a linear function, a graph of linear function in the slope-intercept form, y equals to mx plus b, like this. And in this particular case, m is about 1.01. So as I move one step to the right, I go about 1, just a little bit more than 1.01. And b is this y-coordinate here, 0,1.08, again very close to 1. Let's run it again for a little bit different line. Okay, that's better. This time m is negative. So as I move one step to the right, I have to go down about 1.63 something steps. And then b is negative 1.55, so about 1.5 steps down here, 0, negative 1.55 something. So with slope and the y-intercept, we can determine a line. So those are linear functions, and those are graphs of linear functions. That's not the only way to have a graph of a linear function. Another way to express it is to use the slope point form. Running through a point x0, y0 with slope m, you can write it like this, which I usually do, or in the second method. Both are equivalent because if I flip this y0 to the other side, you're going to get the second expression. And if I flip this negative y0 to the other side, I'm going to get the first expression. So those two are actually equivalent. In any case, here we go. Running through this x0, y0, which is negative 0.62, negative 1.164 something. This is a point, and slope is negative 1.77 something. So we can express any point and a slope, and we have a line. The slope-intercept form can be considered as a special case, y equals to m, x minus 0 plus b. So running through the y-intercept 0, b, which is actually point x0, y0, you can rewrite like that. So you can consider the slope point form is a little bit more general. Another equation that you have to remember is two-point form. So here in slope point equation, apply the slope formula into this m. y2 minus y1 over x2 minus x1. In other words, rise over run. The difference of y coordinate is the rise, and the difference of x coordinate is run. So that's the slope m. And then running through the point x1, y1. Yes, if you put x2, y2 in there, that's okay too. Whatever is more convenient to you. Again, flip this y1 to the other side, we get the second convention. Flip this y1 to the other side, we get the first convention. So these two are equivalent. Here are some examples. Running through these 2 points. Let's run it again. This time running through these 2 points like that. Now let's look at this slope point equation a little bit more closely. The slope is rise over 1, the difference of y coordinate over the difference of x coordinate, and that's often called the average rate of change. Average rate of change is usually more useful for curves, and it actually means the slope of a secant line that's running through a curve. But for a line, we have the same average rate of change everywhere because we have the fixed slope all the time. So no matter what pair of points I select on this line, the slope is the same actually. So average rate of change stays the same. Okay, all right. Now, shall we do some example problems? Okay, here are a couple. Please stop the playback and read through. I got these from the textbook, by the way. Okay, all right. Let's look at the first problem. A strain of E. coli known as Bohr 397 Rec A441 is placed into a petri dish at 30 degrees Celsius and allowed to grow. The data shown in table 2 are collected. Where is table 2? I'll have to open this to see the table 2. Yeah, here it is. The population is measured in grams and the time is hours. Plot the ordered pairs x, y in the Cartesian plane and use the average rate of change to determine whether the function is linear. Let's see. In a graphic paper, times 1, 2, 3, 4, 5, yeah, those are x coordinate, go horizontal. And then these are the population, 0.09, 0.12, 0.16, and so on. And these are the coordinates. And then join those or get a line that fits this data set the best. That's going to be the linear model we are looking for. And as for the average rate of change, let's see, from 0 to 1, the difference of y coordinate is difference of this, and difference of x coordinate is difference of that. So we're going to get this 0.12 minus 0.09 divided by 1 minus 0. So that's the average rate of change in the interval 0 to 1. Let me expand it a little bit. But is that the only way to do it? Well, let's see. Yeah, let's write it like this. Okay, let's write like this. And then how about another interval? 1 to 2. Okay, let's go ahead and do that. 1 to 2. So denominator 2 minus 1. And then numerator change from 0.12 to 0.16. So this is going to be the new quantity, the average rate of change from 1 to 2. If you want to do it for 2 to 3, then you can do something similar as well. So 2 to 3, so 3 minus 2, and then 0.12 is now useless, and then here 0.22, and then you can calculate this, and then you can do times 3 to 4 and 4 to 5, etc. That's not all. If you want to say 1 to 4, if you want to do 1 to 4, okay, so there, and 1 to 4 is 0.29. You can calculate this kind of thing as well. 1 to 4, so denominator is 4 minus 1, and the numerator is 0.12 to 0.29, and let me do just one more. 2 to 5, okay, alright, let's do 2 to 5. So 5.39. As a matter of fact, I've been making some mistakes here, too many zeros, sorry about that. 0.39 and then 0.16. Yeah, okay, we can calculate various quantities here. And if this is really a linear model, if it can be modeled by a linear function, then this quantity, all these values will be very similar to each other. And if you punch those into calculator, then you'll see if they are really similar to each other. I mean, some of them may differ a little bit because, you know, it's coming from experiment, so not everything is right, but they have to be similar. If they are really wildly different, something may be wrong, and if they are systematically different, then something is really, you're really missing something. In this particular case, things are systematically wrong. This slope, the next slope, the third slope, fourth slope, fifth slope, not only they are not very similar, but as a matter of fact, they are increasing. You see, it doesn't look very good. Not only that, you see, they are increasing. Not only they are not similar to each other, but systematically not dissimilar, getting bigger and bigger and bigger. Something is really wrong with this model, and you're missing something very important. So if you join each, then we have line segment, line segment, line segment, and clearly the slope is getting bigger and bigger and bigger. This is not a linear model. This cannot be modeled by a linear function. Just by looking at it, it was a bit hard to tell. This looked actually okay because if you just look at the absolute errors, they don't look too bad. But if you look at these slopes and compare, not only do they not stay constant, about same, but not just they are wrong, not even wildly wrong, they are systematically wrong. So something very different is going on. As a matter of fact, it turns out this is an exponential model. And instead of line of best fit, we can get an exponential fit. And that's something we're going to discuss in chapter 6 in our textbook. So in terms of our lesson, probably lesson 13 when we discuss exponential modeling. Okay, so much for example 2.4, and I wish I had a little bit more time to complete part B, but looks like I'll have to stop here. It turns out part B is gonna be okay model. It's gonna be perfectly fine. I'll stop here in section 2.